Well, let's start with something which we talked about last time. So last time we talked about things such as mass and center of mass. So here's a pretty simple question, maybe. Find the center of mass and the mass for a sphere of radius 2, centered at the origin, where the density function is given by 3 divided by 1 plus the quantity x squared plus y squared plus z squared raised to the power of 3/2. Okay. Well, this is a little interesting. Let's see if we can answer these questions. Well, what do we have? So we have ourselves a sphere. The nice thing about spheres is they're pretty easy to draw. But the other nice thing about a sphere is we're talking about the shape of the sphere, the symmetry. So this sphere has lots and lots of symmetry. And when you have symmetry, you look for that when you're trying to do something like a center of mass problem. So what kind of symmetry do we have? Is there any? I claim that there was some. If it helps, just imagine it's sitting here in three-dimensional space. Is there any nice symmetrical thing across? Usually when we're talking about three-dimensional shape, we're looking for planes. Planes with symmetry. Do you see a good plane? The xy plane is a fantastic plane. Now, so the xy plane here, that's a plane which has symmetry with respect to this shape. But it also has symmetry with respect to density. Now, we should talk about the density for a second. What is it saying? It says the density is 3 over this 1 plus this kind of crazy expression. But if you think about what you have there, it's x squared plus y squared plus z squared to the 1/2. Now, x squared plus y squared plus z squared to the 1/2, what is that measuring? Have you ever seen an expression like that? It's measuring distance. It's measuring distance to the origin. So the x squared plus y squared plus z squared gets bigger the farther from the origin you go. But it doesn't matter which direction. Any direction you go, it gets big at the same rate. So what could we see? Well, it's going to be most dense near the center. And as you move out from the center, it gets less and less dense. So this is a shape where there's a lot of mass near the middle and not quite as much mass near the edges. Things, for example, like planets and stars exhibit this type of behavior. All right, we mentioned the xy plane, which means that wherever our center of mass is has to be on the xy plane, because it's a plane of symmetry. Is there any other symmetry we have going on here? The zy plane. So the zy plane would be this plane. So now I say, okay, there's another symmetry. It's not showing up very well, but okay. The zy plane. If I combine that together with the xy plane, I can say, okay, if I have to be on the zy plane and the xy plane, that means I have to have y equals 0. Any other symmetry? Xz plane. Oh, this is just loaded with symmetries. And if you take just those 3 symmetries together, we can conclude that by symmetry, without doing any calculus at all, the center of mass has to be at the origin. Because that's the only point which has all these points of symmetry. All right, so center of mass, done. Easy, easy. And I probably should start using pens that write dark. Done. Now, what about the mass? Well, that's not so bad. We're just going to integrate over our sphere. I'll call it S for sphere. Our density. 3 over 1 plus x squared plus y squared plus z squared to the power of 3/2 dV. Now, that's what we have to do to find the mass. However, when I look at this integral, one thing sticks out to me. It's hard. I would be challenged to figure out how to even start to begin this integral. So, I'm not going to do it yet. I need to come up with a good plan. All right. So let's think about analogies. In the past, if we were doing something in 2 dimensions, we said, oh, if you had something like an x squared plus y squared, there was a great thing to do. Do you remember what we did if we saw x squared plus y squared? Yeah, we saw polar. Polar was the way. Now we're in 3 dimensions, and we're like, okay, x squared plus y squared plus z squared. Maybe there's a better thing to do. Is there a nice something like polar for 3 dimensions that has x squared plus y squared plus z squared? Yeah, spherical. Okay. So we should try to do this. Let's try to see if we can switch to spherical. All right. So that's our goal. We're going to try to switch to spherical coordinates. Now, how do we go about doing this? The way we switch coordinate systems is we always remember that every integral has 3 important aspects to it. And so we just have to understand each aspect in the coordinate system that we're going to be in. And if we can adapt it to the new coordinate system, we're great to go. So what are the aspects? Well, the first part is the bounds. So we have to describe bounds in terms of what variables we use for our coordinates. So in Cartesian coordinates, we use x, y, and z. In spherical coordinates, we use rho, phi, and theta. So we have to adapt the bounds. Now this is, of course, just a 2-dimensional, but this is how we went from the rectangular or Cartesian towards polar. The next thing is the function. We have to understand what the function is. So we have to adapt it to the variables in our coordinate system. Well, that's usually not too bad because we have rules to say how do you go from one coordinate system to another coordinate system. The last part is the part that you got to remember, which is the how do you break things up. So when we talk about how we break things up, what we're really referring to is let's just perturb our variables a little bit and see what happens. So in other words, I do a little perturbation of y and x, I get a nice little rectangle. And the area of that little rectangle, dy dx. If I perturb r and theta, so I'm doing a little bit of change in r, a little bit of change in theta, what's happening is I'm getting a little bit, not quite a rectangle, but it's sort of a curved rectangle. Remember our picture was it's kind of like a pizza slice, where you have the crust on the end. And we'll get back to that picture in a few minutes. And so, okay, so we have to change the description of the region, we have to update the function, and then we have to do this last part, how do we break things up? First 2 parts aren't usually too bad. So we're going to probably spend a little bit more time talking about this last thing. How do we break things up? Now before we get to cylindrical coordinates, let's do a warm-up. Before we get to spherical coordinates, let's do a warm-up with cylindrical. Now, if you recall cylindrical coordinates, the ideas are pretty simple for cylindrical. It says, take your polar coordinates and add z to it. So in other words, down in the xy plane, you still have r and theta. And then what you have is you have this third aspect, which is z. So z is telling you how far up and down you go. Now the nice thing is we've already talked about polar, so there's not going to be too many surprises here. We'll do a quick few refreshers. If I have x, that's our cosine theta, y is our sine theta, and r is the square root of x squared plus y squared. What we did not write down, but you could if you wanted, is the other equation, which is z equals z. Most people remember that one. So that's why we usually don't write that one down, but it says you don't really have to change anything for z. Now, let's turn to our bits of volume. So you do the perturbation. And if you do that, you get the following pictures. So what's happening is things are being perturbed. So here, you see this angle wedge here. This is saying what happens if you just vary theta a little bit. How much did you change theta? Over here, this is saying how much are you changing r? Now, in other words, you're perturbing r. There's a change in r. And if you look at this part, this is what we used to look at in the polar. We said, okay, what's happening with our change in r and change in theta? We get that little bit of a curved rectangle. And we said that this is approximately r delta theta. Now, we're going to cylindrical, which means we also have a third aspect, which is the z part. And that's going to be represented up there. So that's the perturbation in z. So it's like we're taking the same basic shape as before, that slightly curved rectangle, and then we're just adding some little bit of height to it. So what's the volume? Well, the volume of this little piece is approximately r delta theta, and then delta z, the height. Or, put another way, you say that dv is r dz dr d theta. So that's what you need to remember. So when you're changing your coordinate system and you're going to change to cylindrical, remember that when you talk about your dv, you need to include the r, because that's going to be important. Now, one other comment to make here is you'll notice I specify dz dr d theta. Do you have to integrate in that order? The answer is no. However, I strongly encourage you to make that your default to go to, because this is the most convenient way for you to think about how your coordinate system goes. In other words, start with understanding where does your angle go between, then understand where does r go between. So r is going to go between two curves expressed as functions of theta, and then z is going to go between two surfaces. Okay. So, in general, we can say the following. If I have an integral in Cartesian coordinates over some shape, f of x, y, z dv, well, what does it become? You get your bounds for theta, r, and z. You change your function in terms of r, theta, and z. So wherever you see an x, put r cosine theta. Wherever you see y, put r sine theta. Z stays the same. And don't forget to include the r. And that's it. That's how you change your integral. And now, away you go. Because it doesn't really matter what symbols we use. The integration is still the same. You work your way one layer at a time. Say, okay, integrate with respect to z. Integrate with respect to r. Integrate with respect to theta. What symbols we use, don't change our methods. So let's do an example. So let S, and here S is being a solid, be the square root of x squared plus y squared is less than or equal to z is less than or equal to 2. Find the integral over this new solid of z dv. All right. Well, let's see if we can understand what this solid looks like. So there's two pieces here. Z equals the square root of x squared plus y squared. Do we know what that looks like? Now, the good news is it's something we can draw, so that helps narrow it down. In cylindrical coordinates, we could write it as z equals r, although this probably doesn't necessarily help a lot of people. But why do I say z equals r? Well, one of the things you can think about is what's nice about cylindrical coordinates is it has symmetry around the z-axis. And so, if in doubt, what you can do is instead of thinking of it as like I have x, y, and z, think of it in the following way. I have z and I have r. So, just start with this. Z equals r, what does that look like? It looks like a line. So you graph the line z equals r. So here's the line z equals r. And then what you do is you now spin it, because you have that the symmetry about the z-axis. So if you spin that line, what do you see? You see a cone. So this z part becomes a cone. So we have a cone here. Now, we don't have the cone going up forever. We're going to stop. Where do we stop? Z equals 2. Now, what does z equal 2 look like? It's a plane. It's a flat plane. So essentially what happens is you come up here, let's say that's 1, there's 2, and then you put a plane, a plane here at the top. So the plane z equals 2. So our shape is essentially a cone that stops at z equals 2. Okay, so here's our shape. Now, let's figure out our integral. So we need to do a couple of things. If we're going to do an integral, we have to update our function. So, our original function was z, but that was in Cartesian coordinates. Now we're going to go to cylindrical coordinates, and our new function will become z. That is correct. Okay. The next, the dv. What will dv become? Yeah, it's r dz dr d theta. So that part right there, that's the dv. Now we talk about the bounds. Well, to understand the bounds, one of the things is to say, look, z will be the last part I do. Look down the z-axis. So if I'm staring down the z-axis, what do I see? I see a circle. What can you tell me about the circle? Like, for example, do we know what the radius is? It's a radius 2. Now, you might say, how do we know it's radius 2? Well, the answer says we're combining two facts. We know it's where the surface z equals r intersects with the surface z equals 2. So if z equals r and z equals 2 simultaneously, that means they intersect where r equals 2, which is a circle radius 2. So when I'm setting up my theta and r bounds, that's the picture I'm using to set up. So where does theta go between? 0 and 2 pi. Where does r go between? 0 and 2. And where does z go in between? Z goes between r and 2. Where did the r come from? Well, it came from right here. We actually specify the surfaces. We started at z equals r, and we went up to z equals 2. Now, in this coordinate system, you'll notice I don't have any square roots involved. If I had gone to a Cartesian coordinate system, I'd have several square roots involved. There'd be a square root of x squared plus y squared. There'd also be square roots when I describe the region. But because we picked a nicer coordinate system, we don't have to deal with square roots. And that's great. All right. Well, it said find, so we'll actually finish this problem. What comes next? Well, time to integrate. 0 to 2 pi. We first integrate with respect to which variable? With respect to the z. So r is a constant. So we're going to end up with 1/2 rz squared evaluated from z equals r to z equals 2. dr d theta. We evaluate that integral. Sorry, excuse me. We evaluate that. We're going to get 1/2 r times 4. Oh, well, that's not bad. So that's 4r minus 1/2. And we're going to get r times r squared, which is r cubed. dr d theta. Okay, next. Integrate with respect to r. And if we do that, well, this was 1/2 times 4r is 2r. What's the integral of 2r? It's r squared. Minus integral of 1/2 r cubed. 1/8 r to the 4th, because we're going to add 1 to give us 4 divided by 4. Then we're going to evaluate that from 0 to 2, d theta. Well, okay, so let's see, what is that going to be? Well, 2 squared is 4. 2 to the 4th is 16, so it's 4 minus 1/8 times 16, also known as 4 minus 2, which is 2. And on the other hand, if I plugged in r equals 2, if I plugged in r equals 0, I get 0. I should have specified these are r equals 0, r equals 2. So last integral, well, that's not bad. That's the integral of 2 theta from 0 to 2 pi, giving us our final answer, 4 pi. Good. That's not so bad. And once you have the right coordinate system, it isn't. It's not bad at all. All right, that was our warm-up. Spherical. Okay. So, let's talk spherical coordinates. Now, as a refresher, how do spherical coordinates work? Well, there are two angles involved. Namely, there's the angles theta, which does the same thing as before. So if you think of theta in terms of polar coordinates, it does the same thing as it does in spherical coordinates. It measures how far off the positive x-axis you are. Phi is what measures how far off the positive z-axis you are. So those two angles give a direction. And now you have a distance. And so that distance we mark as rho. Well, we wanted to use r, but we'd already used r. And so we had to come up with something that looks like r. And so that rho symbol kind of is like r, if you were Greek. Then you have this collection of various formulas. Now, we talked about these way back in one of our very first sessions this semester. So, time to remember. So, z is rho times cosine phi, and x is rho times phi, and rho is the square root of x squared plus y squared plus z squared. Ah, that's handy. We might need that soon. Now, if you want to know x and y, you can do one of two things. You can memorize the formulas, which says x is rho sine phi cosine theta, and y is rho sine phi sine theta. But an easier way for me is to remember, I just remember r, because x is r cosine theta. So what you really have here is r cosine theta, r sine theta. So those are the two ways to remember. Now, what's good about spherical coordinates? Well, certainly what's really good about spherical coordinates is it's really easy to describe spheres, and it's really easy to describe cones. So those are our two favorite objects. So if you have things which have spheres or cones, these are a nice coordinate system to consider. Now, we're going to do the same picture that we did last time, or at least a similar picture, which is to say, what happens if I perturb? Well, it's a slightly more complicated picture. So let's talk about where our pieces are coming from. So one thing that's happening is we're changing our rho. Change in rho. So rho is being perturbed. So if you look here, what you're really seeing here is you're seeing sort of a smaller sphere and a slightly bigger sphere. And that delta rho is the change between these two spheres. The next thing that's happening is we're talking about the theta. Well, it does the same thing as we had just a moment ago. How far is the angle changing downstairs? So that's our change in theta. And the last thing is phi, which says, okay, how far from the z-axis are you coming? So I'm perturbing it. So change in phi is over here. That's how much phi is changing. So if I perturb all three of these variables, rho and phi and theta, what do I end up with? Well, what I end up with is sort of a piece of the sphere. Now, of course, it depends on where in the sphere you're at. And so we come to the challenge, okay, what is this volume? Can we figure that out? Well, I hope you'll believe the following. Just go on faith. We'll prove it next time, or at least show you how to prove it. What is the volume? It's roughly rho squared sine of phi, the change in the rho, the change in the phi, and the change in the theta. Now, there's a couple of things that should at least convince us that this is a reasonable thing, even if it's not necessarily an obvious thing. So one of the things that you should look for is you should say, does it make sense that it's a volume? So if I'm dealing with a volume, one of the things that I should have is I should have three lengths involved. Because a volume, we often think of as, like a volume of a box, length times width times height. Or we have units cubed. So do we have three lengths involved? Well, rho is a length. That's there twice. And change in rho is a length. So that's three lengths. And if you look at these other things, sine of phi, change in phi, and change in theta, none of those are lengths. So that's good intuition. We have the right thing going on. At least what we have makes sense as a volume, because we have three lengths involved. The other things you might say is, okay, is it reasonable? So this says the further out you go, the larger the piece should be. I think we would agree if I start moving out, this piece should get bigger and bigger, so it should expand. That's a reasonable idea. Notice that there's no theta in this part. Is that reasonable? Well, theta is a twisting in the xy plane direction. And so if you rotate by theta, it doesn't change our basic shape, it just turns it. Okay, so it's good that there's no theta. Then there's this expression that kind of throws people off, that sine of phi. Does that make sense to be there? Well, think about the picture. So suppose phi was small. Then sine of phi would be small. Now, if phi is small, am I near the z-axis or am I far from the z-axis? You're near it. Because phi is how far I come off the z-axis. So if phi is small, I would be up here. That's where my wedge would be. And you'll notice that when phi is small, it's pretty small, the wedge. It gets big as it goes down. And if you came all the way down until you were near, say, the xy plane, you would see that I would get a bigger chunk. So what should be true is that the small angle for phi should have a smaller piece than a larger angle for phi. And it should really peak at about pi halves. Because after pi halves, you're getting back close to the z-axis again. So at the very least, it's reasonable. Now, of course, that's approximately the volume. And we can say that the dv is rho squared sine of phi d rho d phi d theta. All right. Well, now that you have that, we can change our integral. And what do? You do what you would expect to do. You update your bounds in terms of the variables rho, phi, theta. You update the function. So that's what this means, is it's the updated function. And then just remember, you got to throw in that rho squared sine phi. Okay. Oh. Any questions? Okay. I'll give a question. How can we remember rho squared sine of phi? Because that seems not like an obvious thing. It sounds like something I might struggle to remember. Well, you're in luck. There's a really good way to remember. And after the next minute, you'll never forget it. You can tell your kids, you can tell your grandkids, you're going to be sitting around the fire, roasting marshmallows and say, let me teach you about spherical coordinates. All right. So here you go. You sing a song. Now, most of you have heard this song before. Some of you may not have, if you didn't grow up in the U.S. But there's this song called Row, Row, Row Your Boat. But you change the lyrics. And how do the lyrics go now? Well, it's going to be row, row. See, that's two rows. Rho squared. Sine of phi, sine phi. D rho, d phi, d theta. Now, so those of you who haven't heard it, I'll demonstrate it first. And then we'll sing it together. Okay, so here we go. Just me this time. Rho, rho, sine of phi, d rho, d phi, d theta. All right, did you get that? Okay, are you ready to sing it together? Okay, that sounds like a yes. Ready? And rho, rho, sine of phi, d rho, d phi, d theta. See? That's good. Now, there's, of course, a second part. Merrily, 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 calculus is a dream. You don't have to remember that part, but don't forget that part. Okay, so there you go. Now, the practice. Here we go. Back to our beginning question. Find the mass for a sphere of radius 2, centered at the origin, where the density is the same thing as before. 3 over 1 plus the quantity x squared plus y squared plus z squared to the 3/2 power. Well, okay. So, our picture, we have a sphere. So there's our sphere, radius 2. We know our plan because we said our plan is to figure out how to do this in spherical coordinates. So we're going to do it in spherical coordinates. So our mass is going to be the integral over our sphere of our density dv. So integral Figure out the bounds in a second. We've got to update our density. So what will our density function become in terms of rho, phi, and theta? 3 over 1 plus, so that part's the easy part. 1 rho cubed. Because that 1/2 power, x squared plus y squared plus c squared to the 1/2 is rho. Okay, well that's nice. What will dv be? Rho squared sine of phi. See, remember, rho sine of phi. D rho, d phi, d theta. Okay, all right. Maybe we need to practice that some more. All right. Anyways, okay. Let's do our bounds. Where will theta go between? 0 and 2 pi, because we're going to go all the way around. We're going, as they say, full circle. Now, phi, this will test your memory. Where will phi go between? 0 and pi. Now, why do we stop at pi? Because what happens is when we talk about phi, we're talking about how far we come off the positive z-axis. So phi equals 0 is straight up. Then we start swinging around. At phi equals pi, we're straight down. And that's it. We don't need to go any further. You might say, well, wait a second. What if I were to keep swinging around? Well, you see, the thing is, we have theta that takes care of that. Because if I swing down a little bit and then I spin with theta, it's the same as if I just swung and I overshot. So that's why we don't need to go past pi. Where does rho go between? 0 and 2. Now here's the cool thing. Look at these bounds. What do you notice about all these parts in the bounds? They're all constants. And so we can do the old trick that we did before, which is if our function is nice, pull it apart. And guess what? Our function is nice. So this will become integral 0 to 2 pi d theta, integral 0 to pi sine of phi d phi, and integral 0 to 2 of 3 rho squared over 1 plus rho cubed d rho. Well, first integral. Do we know the integral from 0 to 2 pi d theta? What? 2 pi. Okay, integral 0 to pi sine of phi. Well, what's the integral of sine? Negative cosine. Then evaluate 0 to pi. Okay, cosine pi, negative 1. Then subtract it, so it's minus 1. And then we're going to subtract. When I plug in 0, cosine is 1. Then there's that minus. So it's really, really negative, but so negative it becomes 2. Now we get to this integral. Is that integral something we can do? Yes. In fact, it's something which hopefully we can do in our head. Do you recognize it? If you did a u substitution, 1 plus rho cubed, what would happen? 3 rho squared. So it becomes like 1 over u. So natural log of 1 plus rho cubed from 0 to 2. Plug it in. Well, 1 plus 8 is 9. So you get log 9. Subtract log of 1, which is 0. So we get our final answer is 2 pi times 2 times log 9, or 4 pi log of 9. And that's it for that problem. But we have about 5 or 6 more. Yes, woohoo, indeed. That is the correct thing. Okay, let's try some other problems. Here we go. Rewrite the following integral in both cylindrical and spherical coordinates. So we have this integral given to us, and we want to rewrite it in different coordinate systems. The nice thing is we don't actually have to evaluate it, we just have to rewrite it. All right. Well, probably before we rewrite in anything, what's the first thing we should do? Draw a picture. Figure out what exactly is this? What does this look like? Well, let's see if we can't decode. What are the outer bounds? What variable are we looking at? Well, I'm asking the question. Yes, you're right. It's the y variable. Okay, so this tells us that y goes between minus root 3 and positive root 3. Go to our next layer. What variable am I looking at there? X. So I'm looking from minus root 3 minus y squared, less than or equal to x, less than or equal to root 3 minus y squared. Well, let's piece these things together. I'm in the xy plane. I'm going from minus root 3 to plus root 3. That's very unusual numbers to go between. And then I have x going between these two curves. But what curves are these? So let's start with, say, x equals plus root 3 minus y squared. If you're not sure what it is, what's a logical thing to do? Square both sides. X squared equals 3 minus y squared. Or x squared plus y squared equals 3. So what is that? It's a circle of radius root 3. Oh, very convenient. In fact, both of them are the circle. See, what happens is this is the right-hand side. This is the left-hand side. So the bounds that were given to us were to tell us that this is our region in the xy plane. Now, we've only looked at the outer two integrals, so we still have one more layer to go. But the nice thing is we kind of have a good grasp of the picture now. So it says the following: if you were to look in three-dimensional space, the region you care about is sitting on top of this circle down here in the xy plane. Okay, now we have to figure out where are we? So we go to our last layer, our innermost circle. Or sorry, innermost piece of information. This is a z integral. Sorry, the z bounds. Where does z go between? 1 and square root of 4 minus x squared minus y squared. Now, let's see if we can figure that out. First off, what about this function z equals 1? Or what about this surface? What is it? It's a plane. It is. So I have a plane. Z equals 1. So say here's 1. So just going to go up 1. So on the bottom, I see a flat plane. Okay, so that's my bottom surface. Now let's talk about the top surface. Z equals the square root of 4 minus x squared minus y squared. What is that? It is a sphere. If you square both sides and rearrange, you get x squared plus y squared plus z squared equals 4. So it's a sphere, happens to have radius 2. Okay, my picture's not to scale, but all right. Now, what happens? Well, it's a sphere that comes down, and if you look at it, when z equals 1, what's true? Well, at z equals 1, which is where the surfaces will intersect, I get x squared plus y squared equals 3. Because I plug in z equals 1, 1 squared is 1, move it across. Which means I come down to here. So my scale is very, very bad. Imagine I had a better picture. So this is our top, is our sphere. Okay, so that's our region. It's essentially, I think these are called cross caps, but what it is, it's the top part of a sphere. It's like I took a sphere of radius 2 and I sliced the top of it off. And I want that part. All right. Well, which one first? Cylindrical or spherical? Cylindrical. I mean, it comes first in the problem. Okay, so if I'm doing cylindrical, integral, 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 what would x squared plus y squared become? It become r squared, because remember when we talk about what does it become, we mean in terms of the new variables. So our new variables are r, theta, and z. So x squared plus y squared becomes r squared. dz dx dy, what will that become? R dz dr d theta. Okay, now let's start working through the bounds. What can we say about theta? 0 and 2 pi. All the way around. Because this is the region that we're trying to get the bounds for. This is what you see if you look down the z-axis. Where does r go from? 0 to square root of 3. Where does z go from? Well, what's the bottom? The bottom would be this plane, which in the old system was z equals 1. That's the Cartesian coordinates. In cylindrical coordinates, it becomes z equals 1. Okay, what does the top become? Yeah, see here, we really say, oh look, this is really like 4 minus the quantity of x squared plus y squared. So in cylindrical coordinates, this is the square root of 4 minus r squared. So in some sense, this one's not so bad to switch it to cylindrical, because a lot of it is just set up for it. You got lots of nice symmetry, things work pretty straightforward, no big surprises. Okay, let's do the next one. So this is the cylindrical. So now we get to do spherical. All right. So integral, integral, integral. Let's figure this out. So x squared plus y squared, our function. What will our function become? Well, so one of the things you can do is you can sort of use this intermediate step. It becomes r squared. And one of the things we said is that in spherical coordinates, r is rho sine phi. So if I square that, I'll get rho squared sine squared phi. So that's what the function will become. Now you could, of course, have also said it becomes the quantity of rho times sine of phi times cosine of theta squared plus the quantity rho times sine of phi times sine of theta squared, but it will simplify it down to that. What will the dz dx dy become? Rho sine of phi d rho d phi d theta. Yeah, good. See? We got it. We got it. Good. We're making great progress. Where will theta go from? 0 to 2 pi. The nice thing about the theta is it does the exact same thing in cylindrical and spherical. These are always going to match. If these don't match, something is wrong. So the theta represents the same thing. What's happening as you spin around? And how much do you want? Do you want to go all the way around? Sometimes maybe only just a part of the way around. Now we have to start thinking a little bit more. Let's think about phi. Well, if we think about phi, what's going to happen is we're going to start going straight up, and then we're going to start coming off. And eventually we're going to hit the very corner. And after that point, we're going to completely miss the shape. So what we want to do is figure out, where's that corner? When does our phi come off just enough so we nick the edge? So one of the easiest things to do is to sort of come through and slice the picture. So let's do that really quickly here. So I'm going to do a quick slice. I'll put down, essentially this will be RZ. And I say R because there's nice symmetry here. And what will I see? Well, I have the circle coming down until I hit Z equals 1. So that's what I see. And I know a couple of things. I know that this distance is 1. But I also know something else. I know that this distance here, what is that distance? Square root of 3. And now what am I after? Well, I'm after this angle here. So this angle, that's the angle phi. That's which angle, whoops, sorry. That's the angle which I need to figure out, because that's going to tell me where I stop. Because phi is going to start at 0 and keep going until I get to this angle. Well, what's true? Let's just think about what we know. I know the opposite side and I know the adjacent side. What relates opposite and adjacent? Tangent. So tangent of phi had better be equal to square root of 3 over 1, the opposite over the adjacent. is there a convenient angle where the tangent of our angle is square root of 3? And it rhymes with pi over something. Well, it starts pi over. It's pi over 3. This is the case of the picture's not very good. If I was a better artist, you'd be convinced. That looks like a pi over 3 angle. Right now you're looking like, that looks like 45 degrees. Obviously it shouldn't be, but it's pi over 3. Okay. Well, not done yet. What's left? Got the rho. Now, one of the bounds is easy, and one of them is fun. Which one is the easy bound? Rho equals 2 is the easy bound. Because when we talk about rho, what's happening? We're going to come from the origin, and we go out till we hit the start and go till we hit the end. So I need to know where these surfaces are. Now, the outer surface is the sphere. And spheres, in spherical coordinates, are very nice things. So what will the outer surface be? 2. Rho equals 2. What about the inner surface? What will that be? Well, what is this surface? Z equals 1. What's another way to say z equals 1? Well, let's switch it. We want to go into spherical coordinates. How do I switch z equals 1 into spherical coordinates? Rho cosine phi equals 1, because z equals rho cosine phi. But I need to get to rho equals something, because my bounds are from rho equals to rho equals. So I don't want to leave it as rho cosine phi equals 1. I want to write it as rho equals secant phi. So that is my lower bound. So integral of 0 to pi, integral of 0 to pi over 3, integral of secant of phi to 2. And then the integral, we can leave it just as this. You could also write it as rho to the 4th sine cubed. Now that's doable in that you can do it. We're not going to. So we're going to pause here. Okay, and now let's continue. So more examples. It's really important just to keep practicing. You're going to see that there's a lot of common ideas. We're going to do the same things over and over again. And the more we practice, the better we get. So here we go. Find the center of mass for the top half of the unit sphere where the density is 4 times the square root of x squared plus y squared plus z squared. Now looking at this, we have a couple of suggestions that this is probably a good idea to work with spherical coordinates. The first clue is the word sphere. It's pretty compelling when you see a sphere. Think spherical. It doesn't have to be. But almost more compelling is the fact that you see the square root of x squared plus y squared plus z squared. See, if we were to switch into spherical coordinates, what would happen is this would become 4 rho. And that's a pretty simple expression. Okay, so what do we do? Well, we want the center of mass, and our shape is sitting here in 3-dimensional space. Now, it's not the whole sphere, it's the half of the sphere. So, in particular, what's going to happen is we have this base is the xy plane, and then we're coming up. So this is our shape, our half of our sphere. Notice it's the top half. All right, so we want to find the center of mass. Now, a couple of things that we should, of course, automatically know. When we look at our shape here, one thing to note is that this shape has a lot of symmetry. And in particular, it has a lot of symmetry with respect to the z-axis. So if I look at the z-axis, I see that this shape, if I rotate around the z-axis, I maintain the same shape, but I'm also going to maintain the same density. So this is an axis of rotation. And because of that, what we can conclude is that the center of mass lies somewhere on the z-axis. So that tells us that x bar and y bar are going to be 0. So we used the shape to help narrow our problem down. So now we have to find z bar. Now, unfortunately, it's not going to be as free as the other two computations that have been the x bar and the y bar, but that's okay. If I'm looking for my z bar, I know that the way I compute it is I take a ratio. the moment with respect to the xy plane divided by the mass. So that's where we're going to be putting our energy on. So let's start with the mass. That's usually the more straightforward one. To find the mass, we're going to integrate over our solid density dV. So switching to spherical coordinates, integrate, triple integral, going to give ourselves some space to write down the bounds. Our density is 4 rho. And our dV, well, rho sine of phi, d rho, d phi, d theta. All right, good. Now, what are the bounds? Well, theta, it's easy to see because we go all the way around, 0 to 2 pi. Phi, where does phi go from? Well, phi starts up the positive z-axis, and then it starts coming down. Well, I'm going to come down until I hit the xy plane. I don't need to go below the xy plane. So phi equals 0 is straight up, and phi equals pi halves is the xy plane. So phi goes from 0 to pi halves. Now, what about rho? Well, rho says, how do you relate to the origin? So from the origin, if I go in some direction, I'm going to go until I hit my sphere. So that means I'm going to go from rho equals 0 out to rho equals 1. Whoops, I almost said rho equals 2. It's the unit sphere. You see unit here. This says that rho equals 1. All right. Well, we've got our pieces in place. So this becomes integral. In fact, not only do we have our pieces in place, we can pull our pieces apart. Integral 0 to 2 pi d theta. Integral 0 to pi halves. Then we have sine phi. And then we have integral 0 to 1 of 4 rho cubed d rho. So the first integral, 2 pi. Second integral, well, minus cosine phi from 0 to pi halves. Cosine of pi halves is 0. Cosine of 0 is 1. So it becomes 0 minus minus 1, also known as 1. And this integral, well, that's nice. Rho to the fourth from 0 to 1, which gives us 1, which means our mass is 2 pi. Now, that's our mass. That's not our center of mass. We need that when we're going to find the mass. Now, next up, we need to find the moment here. Okay, so let's talk about what changes. Well, the moment, the big thing about the moment is you add in a distance aspect. So here, our distance is with respect to the xy plane, or z. So our moment has the following form. Integral over our shape, the integral of z dv. So it's going to be a very similar thing. We're going to switch everything into spherical coordinates. The thing to remember is that in spherical coordinates, z is rho cosine of phi. So what will this become? Well, integral 0 to 2 pi, integral 0 to pi halves, integral 0 to 1. Our bounds are still the same because it's the same shape. Now, what happens? Well, I'm going to get rho cosine phi. That's my z. Then I'm going to get my delta, my density. That's 4 rho. And then I get my dv. Rho sine of phi, d rho, d phi, d theta. Oh, easy. Good. The same idea still works. We can still pull things apart. So what do we get? This becomes integral 0 to 2 pi d theta, integral 0 to pi halves of sine phi cosine phi d phi, and integral 0 to 1 of 4 rho to the fourth d rho. Now the first integral, still 2 pi, that's not so bad. The second integral, there's lots of ways to do this one. Now one way you could do this one is to say, well, sine phi cosine phi is a half sine of 2 phi. Another thing you can say is, well, suppose for a moment we said, let's let u equal sine phi, then du would be cosine phi d phi. So it becomes u du. So we say, aha, that means that this is the integral of 1/2 sine of phi squared. And I'm going to evaluate from 0 to pi halves. And the last integral, that's not so bad. That's 4/5 rho to the 5th. Evaluate from 0 to 1. So from here, plug in pi halves. Sine of pi halves is 1. Sine of 0 is 0. So this becomes a half. And here, well, plug in 1, you get 1 times 4/5. Plug in 0, you get 0 times 4/5. So you get 4/5. So what do you end up with? Well, 2 pi times a half is pi times 4/5 gives us 4/5 pi. That's still not our z coordinate, but to finish it off, we can say that z bar is the ratio, the moment with respect to the xy plane, divided by the mass. Now, very conveniently, the pi's cancel, and 4/5 divided by 2 is 2/5. And that's the z coordinate, or z, if you want to sound very British, very fancy. Would you like some tea with your answer? How about a z? All right, 0, 0, 2/5, put it all together. That's the answer. Now, we should always pause and ask the question, is this reasonable? All right, well, let's think about it. Is this reasonable? Well, one of the things that should be reasonable is that 2/5 should be somewhere in this shape. Notice that where did we go? We go from z equals 0 is the bottom, up to radius 1. And so that's good. 2/5 is somewhere between 0 and 1. If we had gone an answer of 5, way up here, oh, that's bad. 2/5 is reasonable. And also, really, it's almost halfway in between. And that's about right. It's about, 0.4. So a reasonable answer and a reasonable process. Okay, well, that's good. Good. One more problem done. Let's try another one. Evaluate the following integral by first converting into spherical coordinates. Well, that's nice. It told us what to do. It says we need to convert into spherical coordinates. So let's figure out what our region is. It's not so obvious staring at this what our region is. So we start by deciphering. We can see on our outer integral, that's associated with the x. So we know that x goes between 0 and 1. All right, that's good. The next layer is associated with y. So I'm going from y equals x, and then I'm going to go up to y equals the square root of 2 minus x squared. Let's see if we can figure out what these are. So if I'm in the xy plane, so I'm going from 0 to 1, there's 1, and I'm going from y equals x, here's the line y equals x, and then I have this curve. Well, let's look at that curve, y equals the square root 2 minus x squared. That's the same as, of course, y squared equals 2 minus x squared, or x squared plus y squared equals 2. So that's a circle, and it's a circle with radius square root of 2. So let's say square root of 2 is somewhere here. And what will happen is, if I look at it, it's going to come when x equals 1, I'm going to get y equals 1. So it's going to actually intersect something here. So this is a nice wedge of a circle. And so if we were to shade in our region here, we're going from the bottom, which is y equals x, up to the circle between x equals 1 and 2. All right, so there's our region in the xy plane. Those are our two outer integrals. But of course we have a third layer, our innermost layer, z. So what do we know about z? Well, let's switch colors actually, since just to emphasize the idea. We have the square root of x squared plus y squared is less than or equal to z, is less than or equal to the square root of 4 minus x squared minus y squared. Now these should be somewhat familiar. We've seen these before. This first one, z equals the square root of x squared plus y squared, also known as z equals r, that's going to be a cone. This other layer here, this is z equals the square root of 4 minus x squared minus y squared. Well, whoops, that's a z, not an x. becomes, if you rearrange it, x squared plus y squared plus z squared equals 4, which means that we're going to go from a cone up to this surface. Now this surface happens to be rho equals 2, because x squared plus y squared plus z squared is rho squared equals 4 is rho equals 2, which is a sphere. All right, let's sketch what's going on here in 3 dimensions. So here we go. X, y, and z. If we take this picture right here, what it translates into is it's going to hit here at y equals root 2, and it's going to be a circle downstairs until we go to about 45 degrees, so that this wedge here translates into this part here. So that's just on the side. That's just, again, only in the xy plane. Now we have to draw the rest of it. Okay, for that we need to think about what the shape is. So I'm coming up and I have the following. I have a cone. So we have a cone coming up. And then that's, of course, going to be spinning around. And then the other thing is that we have here is a sphere of radius 2. And that's going to be coming down. All right, so I have my sphere and I have my cone. And where do they intersect? Well, where do they intersect? Well, what has to be true? They're going to intersect when the following is true. Namely, when x squared plus y squared, so let's do some notes up here. The intersection, we have to have that x squared plus y squared would be equal to z squared, which would be equal to 4 minus x squared minus y squared. If you rearrange that, what you get is you get that x squared plus y squared will equal 2, because I can add the x squared plus y squareds and then divide by 2, which means that the intersection is actually this circle here. So it's going to intersect right above there, and then what's going to happen is it's going to turn. And so we also have this point here, and we're turning. So we have a cone, and so we have a sphere. All right, so it's kind of a little bit interesting shape here. All right, so what do we have? Well, it's good to sort of get a grasp of our picture. We can say that we have the following shape. We have the top surface, that's our sphere, and then we have our bottom surface, which is our cone. So there's our cone. Okay, and we're over this region. Now we're ready, we think. Okay, let's work on setting up our integral. Okay, so the integral will be integral of z squared. Well, we've talked about z. Z becomes rho cosine phi squared. dz dy dx. dz dy dx is dv. So that's going to become our rho sine of phi d rho d phi d theta. Yeah, so this is dz dy dx becomes rho squared sine phi d rho d phi d theta. Good, good. All right. Now, time to start thinking. What can we say? Well, let's start with theta. Now, theta is, we can look in the xy plane. It does the same thing as theta in polar. So we look at this. This is the line y equals x, which means that this angle, that's pi fourths. So that's where we're going to start. Then we're going to keep going up until we hit the y-axis. Well, that's pi halves. So theta, pi fourths to pi halves. All right, so that's theta. Now let's go to our next layer, phi. Well, phi, we can just think about the picture. In fact, let's just look at our picture if we look in a slice. So if we can look and say the RZ slice, what we're going to see is we're going to see this R equals Z, or Z equals R. So we have this coming off here, and then of course we have this sphere, 2, circle coming down, and so that's our shape, our three-dimensional shape. It's essentially this shape, but we rotate it, but not, instead of rotating all the way around, we're only going to rotate about 1/8 of the way around. All right, so let's say, where does phi go from? Well, in the diagram here, phi equals 0 is straight up. And what's going to happen is we're going to keep going, we'll keep going, we keep going, until right here. Now, how far off the positive z-axis did we go? The answer is we went pi fourths. That's the angle off the positive z-axis. So when I'm asking for the phi, it's going to be 0 to pi fourths. All right, now we're almost done. Where does rho go from? Well, we always think about rho as coming from the origin. So we're going to say rho comes out, and we're going to go until we hit this outer surface. Well, the outer surface is a nice surface. It's a sphere. Rho equals 2. So it's 0 to 2. And now we say, this is great. It's one of our favorite kinds of integrals because it has the following property. If you look at the bounds are nice. They're all constants, which means we're going to have the ability to pull the integral apart. So let's pull our integral apart and see where that takes us. This will become integral from pi fourths to pi halves d theta. Then integral 0 to pi fourths of cosine squared of phi sine of phi d phi. And last, integral 0 to 2 rho squared, and another rho squared makes rho to the fourth d rho. Now the first integral, that's pretty easy. We can do that one without having to do any work. It's 1 from pi fourths to pi halves, which is the difference between the endpoints. That's pi fourths. Now the second integral, that one's slightly more subtle, but not too bad, because what happens? Well, it's set up in a nice way. If you let u equal cosine phi, then what you get is that du is negative sine phi d phi. Well, you can move the minus across so that this would become the integral of minus u squared du, or minus 1/3 u cubed. So that this integral here is going to become minus 1/3 cosine cubed phi, evaluate from 0 to pi fourths. And now the last integral, well, that one's not so bad. 1/5 rho to the fifth from 0 to 2. So let's do our next iteration here. Pi fourths, cosine of pi fourths. Well, cosine is root 2 over 2. So if we multiply this out, the minus 1/3, just for a second, we'll put it to the side. Root 2 over 2 times root 2 over 2 is a half, times another root 2 over 2 gives us 1/4 root 2. So that's if I plug in pi fourths. Subtract, plug in 0. Well, cosine of 0 is 1. So 1/4 root 2 minus 1. Well, the minus helps make that positive, so if we put the minus through, so 1 minus 1/4 over root 2. Over here, we're going to get 1/5 times 32. And then subtract 0. Okay, well, let's see what happens. We have pi fourths times, here I'm going to have 1/3, and let's go ahead and pull out a fourth. So I'm going to pull out a fourth, and if I do that, what's going to be left is a positive 4 from the plus 1, and a minus root 2 from the first term. Then finally I'm going to have another 1/5 and a 32. Well, here's some nice facts. 4 and 4 become 16, and 16 goes into 32. So if we do that math, which we do really quickly, we get some nice cancellation. And so what do we end up with? We get 2 pi over 15 times 4 minus square root of 2. Done. Done. All right. Well, that wasn't so bad. Certainly probably simpler than trying to deal with all those square roots that would have inevitably come up if we had tried to do this using the integral as written. It's nice to have choices. It's nice to have options. All right. Let's do another one. Here we go. Ah, this one. I can already tell I like this one because my eye is drawn to the arctangent. Let D be the solid where 0 is less than or equal to y, is less than or equal to x, and 1 is less than or equal to x squared plus y squared is less than or equal to 9. So let's talk about just these first two facts here. What do those tell us? Well, if we look at it, we can kind of quickly spot what's happening. Y equals 0 is the x-axis, and then we have this line y equals x. So I'm somewhere between this part. So I'm in that part right there. But we also know 1 is less than or equal to x squared plus y squared. Well, x squared plus y squared equals 1. That's a circle of radius 1. Let's just sketch that. All right, and x squared plus y squared less than or equal to 9, that's a circle of radius 3. Well, that would be somewhere over here. And again, we can just sketch part of it. So here we go, radius 1, radius 3. I've got to be in between those two. So I've got to be in this wedge, and I've got to be between two circles, which means that in terms of where I am in the xy plane, I am in a shape that looks something like that. Okay, so there's my shape. Now, just only the shape by itself suggests this is probably going to be a nice problem in non-Cartesian coordinates. So we already have a hint, just the shape, that we should go non-Cartesian. It's not obvious which way we should go yet, but all right, it's in the back of our minds. We're thinking about it. Now, we're told that 0 is less than or equal to z is less than or equal to arctangent of y over x. And at this point, our usual reaction should be something along the lines of, what? Arctangent y over x. What is that? Well, let's think about what that is. We know we should be switching to a different coordinate system. So let's switch to a different coordinate system. We've done a lot of problems with spherical. I think it should also be good to try cylindrical. And there's nothing here that shouts spherical. Something that shouts spherical should be spheres, or a nice cone, or an x squared plus y squared plus z squared. If you don't see that, it's usually easier to go with cylindrical. So let's think about what this would become in cylindrical. So here we could say, well, that's arctangent of y becomes r sine theta, and x is r cosine theta. Now, if we stare at this, don't have to stare very long, the r's cancel. Sine over cosine is tangent. So this is arctangent of tangent. Well, that's the nice thing about arctangent and tangent. They undo each other. So this becomes theta. Ah, nice. So what we're really saying is that 0 is less than or equal to z is less than or equal to theta. So that's a nice expression in cylindrical coordinates. Now the question you might have is, well, what does that look like? Well, let's think about what's happening here, and then we'll try to sketch a better picture. At this point, if I'm on the positive z-axis, I have theta equals 0. As I move along, I'm going to eventually get to this point where I'm going to get to theta equals pi fourths. So what happens is, as I'm moving in this direction, as I'm moving up, my theta increases. So it's almost like we have a ramp that's coming up. And in fact, more than just it's almost like, it is a ramp. That's what this shape will be. So we will draw a picture. It may not be the most convincing picture, but we don't need to be the most convincing picture. So what do we have? Well, if we look at our shape, what we have down here is it's going to come, and so we have that our shape downstairs, this translates into our three-dimensional picture. There's our base, and now what's going to happen is that as I come along, I'm going to be moving up. So I'm going to swing on up. So upstairs here, I have the following. So I'm always a constant height as I move along. So I have this ramp coming up. Now, even if we don't have the most convincing picture, well, at least we have a solid idea of what we're doing. All right. Good. Well, now that we understand our basic idea, what our shape is doing, we're ready to go. We're asked to find the total mass. So finding total mass means we need to integrate density. So we're going to integrate over our solid, which is now called D, our density, dV. So this is going to become the integral. Give ourselves some space to write our bounds. Density, well, this is in Cartesian coordinates 3z, but in cylindrical coordinates we get 3z. Another nice thing about this choice of cylindrical is it's very easy to adapt our density. Our dV, that's r dz dr d theta. Now we're ready to start talking about our bounds. Well, we can use our picture here. Theta is going from 0 to pi fourths. R, well, always think about it coming from the origin. So I come out till I hit my first curve, and then I go till I hit my second curve. So I'm going to go from r equals 1, circle radius 1, to r equals 3, circle radius 3. And then my last layer, my z, well, I'm going between z equals 0 and z equals theta. So 0 to theta. And now we're ready. We're ready to go. Okay, notice I can't pull this integral apart, at least not all the way, because the theta there. The theta, that's the function. You can only pull the integrals apart if there's no functions involved. That's all right. We can still do the integrals. These are nice integrals. So let's start working our way through it. First we integrate with respect to z. So this becomes integral 0 to pi fourths, integral 1 to 3, and when I integrate with respect to z, we're going to get 3 halves rz squared, evaluated from z equals 0 to z equals theta, dr d theta. So let's do that evaluation. 0 to pi fourths, 1 to 3, and nice thing is we plug in 0, we get 0, we plug in theta, we're going to get 3 halves r theta squared. Dr d theta. There we go. Okay. Now we can actually pull it apart because, you know, everything's good to go. Nothing's mixed together. So this becomes integral 0 to pi fourths times theta squared d theta. And then, of course, don't forget the 3 halves. I'll put that out in front because I don't know where it goes with yet. And then we have the integral from 1 to 3 of r dr. So, let's see, this becomes 3 halves. And then the integral of theta squared, that's going to be 1/3 theta cubed. And then I'm going to evaluate from 0 to pi over 4. And then I also have integral of r, 1/2 r squared. I'm going to evaluate from 1 to 3. So we can do a couple of things. The 3's cancel. So what do we get? We get this is 1/2 theta cubed. Well, that's pi cubed over 64. And subtract 0, that doesn't do anything. Then come to the next term. Well, that's another 1/2. And then we have r squared, 3 squared, 9. Subtract 1 squared, 1. Okay, 9 minus 1 is 8. Well, 64 goes into 8. And So what do we get? Well, if we treat this as 8, we can do something like, I can divide a 2 and a 2 and another 2. And that makes 8 downstairs, it's an 8 upstairs, which leaves me with pi cubed divided by 32. And that would be the mass. Okay, good. Nice. This is a fun problem. This was a problem from an old exam. And I like that problem. It's good stuff. All right, well, do we have more? I think we have maybe one more. Okay, last problem. Set up, but do not evaluate an integral in spherical coordinates to find the mass of the object which lies above the cone z equals square root of x squared plus y squared, and inside the sphere x squared plus y squared plus z minus 1 squared equals 1, where the density is the square root of x squared plus y squared. Okay, let's just sort of start figuring out what we need to do. First off, we know we're going to go to spherical coordinates, the clue being the word spherical. They tell us we're going to go to spherical. So we need to sort of figure out how to do that. So there's a couple of things. Let's talk about our integral. So our integral is going to be the mass is you integrate your density over your solid dV. Now the good news is that the density, we can figure that out. In Cartesian coordinates, that's square root of x squared plus y squared. But we oftentimes think of that square root of x squared plus y squared as being r, and then if we go one more step and say, but I want that in spherical coordinates, r becomes rho sine of phi. All right, so we get rho sine phi. Now that's the density. What about the dV? The dV, well, rho, so that's rho squared, sine of phi. Then you get d rho, d phi, d theta. Okay, good. So there you go. There's our dV. Rho squared, sine of phi, d rho, d phi, d theta. All right, good. That takes care of the density, that takes care of the dV. We're almost done. We're almost done. Because if you think about it, what do we have? Every integral has 3 parts. So this integral, we're going to get the integral, density of rho sine of phi, and dV is rho squared sine of phi, d rho, d phi, d theta. Now, of course, we would multiply these together, but for right now, we're just worried about setting these up, and so we don't need to do that. So why aren't we done? Well, the bounds. We've got to figure out the bounds. So let's think about what our shape is doing here. One of the things to note is that we're going to get a lot of symmetry going on here because there's no restriction in terms of moving around the z-axis. So let's talk about our shapes. We have the cone z equals square root of x squared plus y squared. So if I were to go here and to draw my axes, what I would see is if I were to graph that, I would get a very nice simple cone coming down at a good angle. So there's my cone. And of course, what do I want? I want to make sure I'm above it. So I'm on this part of the cone. Now, I have some upper bound. I don't know exactly what it is, but I'm going to be there. Now, what is this telling us about? If we look at the picture and think about it, it's telling us the following information. You see, it's telling us about phi. Phi equals 0. That's straight up. And what's happening is I'm coming down, and I'm coming down with phi. And I stop at this point. Well, what is that phi? The answer is that that's going to be phi equals pi fourths. Now, you might say, yeah, because we keep doing the same example over and over again, what would happen if it's a different example? And the answer is look at a slice. If you're not sure, see what it looks like in the slice. Now, in our case, think of the slice as being r and z. And you'll see that this becomes, right here we go, z equals r. And so we have this nice line, z equals r. And so that's a 45-degree angle. If it was z equals 2r, we'd have a slightly shallower phi. Phi would have a smaller range. Z equals a half r, phi would get a little bit bigger, and so forth and so on. But the nice thing here, that's an angle of pi 4. So notice I'm coming off the positive z-axis. That's how I determine my angle. Okay, so we know a couple of things. Well, we know phi is going to go from 0 to pi 4. We also know there's no restriction on theta, because we never say, okay, x has to be positive, y has to be positive. There's no restriction. Every time we see x or y, it's always of the form x squared plus y squared. That tells us we're going to have a nice rotational symmetry. So for our bounds, we already know a couple of things. We know theta is going to go from 0 to 2 pi, go all the way around, and we know phi is going to go 0 to pi 4. So we're almost there. The last thing is this sphere. Notice something different though. See, normally when we talk about spherical coordinates, we talk about sphere centered at the origin. So if I have a sphere centered at the origin, that has a nice expression. Namely, this is something of the form rho equals some number, let's say c. But this is not centered at the origin. So let's figure out what that sphere is. Well, in terms of the diagram, if we think about it, we can actually see this because we're used to this coordinate system. In Cartesian coordinates, this says you take your sphere, and what you've done is you've moved the center up to 0, 0, 1. So our center is at 0, 0, 1, and our radius is 1. So what we have here is we have a sphere that is sitting on top of the xy plane. So that's the picture of what the sphere is. If we were to cross our eyes and meld these two pictures together, what you would see is that the cone would be coming up and it would be just touching the sphere, intersecting with the sphere at the equator. So we're really cutting those parts of the sphere off. So our real shape is the following. If we put everything together, we get a cone coming up to height 1. And then, on top of that, we have a half a sphere. So it's almost like if you've ever had like an icy or some shape where you have like maybe an ice cream cone, depending upon the type of cone you have. All right, so there we go. That's our shape. Now, what can we say? Well, we've got to figure out what's happening to our R. What is R doing? Well, R, always think about it coming out from the origin. Comes out from the origin, and then we're going to go until we hit this top surface, this top sphere. Sorry, I said R. I should have been saying rho. Rho comes out from the origin until we come out and hit that top surface. So I go from rho equals 0. The last piece of the puzzle, to finish it off, what's the sphere? So let's stare at this equation. X squared plus y squared, and here I'm going to actually expand. Z squared minus 2z plus 1 equals 1. The reason I expand is I say x squared plus y squared plus z squared in spherical coordinates is simple. That becomes rho squared. Now I have to handle the 2z. Well, z becomes rho cosine phi. The ones, they cancel. So this also says that rho squared is 2 rho cosine phi. Divide out by a rho, you get rho equals 2 cosine phi. Now if you say, boy, that seems familiar, you might see that we've done this before, where we've done in polar coordinates r equals 2 cosine theta. So this 2 cosine phi, that goes up here. That's the upper limit. That's where we're going to hit our surface. And we just had to set up. We didn't have to evaluate. Because I suspect if we were to go through and work this out, there would be at some point a messy evaluation. But that's okay. Even if it's messy, there are ways to do it. I mean, computers can do it, but that's only if we know how to tell the computer what to do. And that's what we're learning. All right, well, how do you get better at these problems? The answer is you do more. The more you do, the better. we've done some. Look for basic shapes. Look for, your spheres. Look for your cones. When you get into cylindrical coordinates, you can do other shapes like bowls work out really well. But use your intuition. Understand things. Get a good grasp of the geometry. The reason why these problems are always popular is because they test how well do you know geometry. And really, at the end of the day, that's the part of Calc 3 that's most challenging. All right. Well, we talked about cylindrical and spherical. You might wonder, are there any other coordinate systems? The answer is there's many, many coordinate systems. But that's for next time.